Okay, we're going to do a lesson on continuity. So when you think about continuity in the most simplest terms is function is continuous if you can draw it without lifting your pencil. Okay, so in a really simplistic terms, that's what continuity is. So there are no breaks, so like holes, no jumps, no asymptotes, no vertical asymptotes. Okay, that's what continuity refers to. So, when we're talking about continuity, there's two types of continuity that they talk about within calculus. One is called removable, and that refers to a hole. Even if the hole is redefined, that refers to a hole. That's called removable discontinuity. Non-removable is either a jump or a vertical asymptote. Okay, so it's either a jump or a vertical asymptote. So you're going to be asked to do a couple things on delta math, and so it'd be a problem similar to this. It says, the graph of the function is defined below. State all the values of x in the open interval for which the function has removable discontinuity. So removable discontinuity is a hole, and so that's what we're looking for. We're looking for places where there's a hole, because clearly, that's discontinuity, and that's discontinuity, and that's discontinuity, and this is discontinuity. So all those are discontinuity. These two are non-removable. These two, both of those, are removable. Okay, so when we're asked where is this non-removable, where is this removable discontinuity? It's when x equals -3 and when x is equal to 1. So both of those places would be answers to that. State the values of x, which the function is discontinuous. And we're going to go a little bit further. We're going to talk about what kind of discontinuity. Clearly, there's discontinuity. There's discontinuity. There's discontinuity, and that's discontinuity. So there's a bunch of places that those are discontinuous. These three are what we might term as removable. This one is non-removable. So this function is not continuous at -4, at -1, at 2, and at 3. So all of those places is where this function is not continuous. There is a break in the graph. All right. So if we were to formally define continuity and more, that was a pretty simplistic way to look at continuity, but let's formally define continuity. In order for f to exist, in order for f to be continuous at some value x equals c, the following conditions need to be met. Okay, so in order for this thing to be for a function to be continuous at some value x equals c, here's the following things that need to be met. First of all, the limit as x approaches c of f of x must exist. And it really needs to approach the same value from the left and the right. Okay, so it has to approach the same value from the left and the right. The second thing that needs to be true, f of c must exist. Okay, so f of c must exist. And then finally, third thing is f of c has to equal the limit as x goes towards c of f of x. So they have to be the same value. So those are the three conditions that have to be met. If you meet those three conditions, then all is good. So let's look at a problem. Let's look at a problem right here. Okay? So this is use the definition of continuity to determine whether, oops, sorry, I'm going to get so I can see it. There. Use the definition of continuity to determine whether the function f of x graphed below is continuous at x equal 2. Well, you right off the bat should say is not continuous at x equal 2. But let's talk about those things. Let's talk about these. And you could say, the limit as x goes towards 2 of f of x does not exist. It doesn't exist because the limit as x goes towards 2 from the left side is equal to -1, but the limit as x goes towards 2 from the right side is equal to -5. So that limit doesn't exist. Furthermore, on this particular one, f of 2 does not exist. There's no place that f equals when x equals 2 that f has it even a value. So this is not continuous. So f of x is not continuous at x equal 2. So that's where we are. That's how you would do that. This particular one doesn't work. So let me show you another example, see if another one is a little bit better, or a little different, actually. Let's look at this one. So now we're worried about -5. So clearly, when you look at this graph, when x equals -5, which is right there, you could say, oh yeah, that function's continuous. Well, let's look at it. Let's look at the limit as x goes towards -5 of f of x is equal to 6. That limit right there at the top, it's equal to 6. We know f of -5 is also equal to 6 because it's right there. Okay? So, since the limit as x goes to -5 of f of x is equal to f of -5, which is equal to 6, yes, we do have continuity when x is equal to -5. So we have to check all three things. Does the limit exist? Does the function exist? And are they the same value? If you go through that, you should be good to go. Hope this makes sense. That's all the examples I had. Hope this makes sense. Good luck.